In this lesson, we'll talk about concept of function, domain, and range. First, let's talk about relation. A relation is any set of ordered pairs, any set of points in a plane. An ordered pair that can be visualized as a point in a plane consists of independent variable, sometimes called input x, and dependent variable, sometimes called output y. So we are saying that x and y are in relation. Like two people calling each other, they communicate. We can say they are in relation of having conversation at this particular moment. Let's look at some examples of relations. For instance, households assigned to each postman in Abbotsford area. So what would be the input and what would be the output? Remember, output is depending on the input. Since we assign households to each postman, then the input is a postman and the output is households that are assigned to him or her. Notice that in this relation we may have lots of households assigned to one and the same postman. Another example, points in the system of coordinates that are equidistant from the origin 0, 0 and the point 4, 0. Let's see those points. 0, 0 is here and 4, 0 is over there. Can we guess a point that is exactly equidistant from these two given points? Well, the easiest such point would be 2, because 2 is 2 steps from 4 and 2 steps from 0. Can we have more points than that? Where are they? That's a good place to pause the video and try to find those points on your own. So I hope you've got points like 2, 2, 2, 1, 2, 3, 2, negative 2. Okay, let's list some points that belong to this relation. For example, 2, 0, or 2, 1, or 2, negative 1, and so on. 2, 5, and we can list infinitely many such points. Actually, any point on this vertical line, x equals 2, is equidistant from these 2 points. Well, let's check this. If I will take any point on this perpendicular bisector of the segment from 0 to 4, let's say somewhere here, and I measure the distances from p to 0 and from p to 4, you can see those distances displayed here. No matter where is my point, the distances are constantly the same. You can observe these two numbers and they are always the same. Even if we cross the segment to the other side, they are constantly the same. Why it is so? Well, since we are talking about perpendicular bisector, first of all, it is perpendicular to the segment 0, 4, so we have right angle here and there as well. Secondly, it bisects the segment 0 to 4, so these two distances are exactly the same. Thirdly, the segment P2 is common for these two small triangles, so we can mark it as common. Therefore, by the side angle side property of triangles, these two triangles are really congruent, which means that the sides P0 and P4 must be exactly the same as well. That shows that any point on this perpendicular bisector has the desired property. It is equidistant from 0 and 4. What about points that are outside of this line, somewhere in the plane? For example, if I pick a point Q somewhere on the plane and start observing the distances between Q and 0 and Q and 4, which are displayed over here, you can notice that those distances are actually different. They are not the same, unless the point is actually on the line. But when we go to the other side, it's still different. And in the bottom, the numbers are different and different. Therefore, only points of the perpendicular bisector are in our relation. So this relation contains infinitely many points. Let's see the next example. Correspondence of knowing each other among a randomly selected group of people. So we have already one representation here as a set of ordered pairs of numbers. We could visualize the set of ordered pairs by graphing it in a system of coordinates. So for example, we can say that the person 1 knows person 2. So 2 will be on the y-axis here. And place the point 1, 2. Then 2, 1. Okay, person 2 knows person 1. So far, this relation is actually reflexive, meaning that 1 knows 2 and 2 knows 1. They both know each other. Let's try the next one. 2 is related to 4. That means 2 knows 4. Okay, 2, 4 will be here. That will be 4. Then 2, 5. 2 also knows 5 over here. And 3, 5. Number 3 knows 5. That will be this point. And finally 5, 4. Person number 5 knows person number 4. Here it is. So this set of points represents certain relation. How else can we visualize this relation? Well, we can use arrow diagram. For example, if I mark all 5 people, number 1, 2, 3, 4, and 5, and now we can record the relation who knows whom by using arrows. For example, person 1 knows person 2, so I will put an arrow like this. And then person 2 knows person 1, so the arrow goes backwards like this. Then person number 2 knows person number 4, so the arrow goes this way. 2 knows 5 over here. 3 knows 5. Oh, we could draw it like this. And 5 knows 4 over here. So we end up with a graph, arrow diagram, that gives us a little bit more of dynamic between those people, who knows whom. Here we have another example. Distance d driven in a certain time t, assuming the constant rate r, which is 20 kilometers per hour. The formula that relates distance with time is distance is rate times time, but the rate is given, so it's 20t. Okay, as soon as we have a formula, we can easily develop a table of values and we can easily graph it in a system of coordinates. Let's do it. If t is 0, then the distance driven in no time is also 0. If t is 1, well, then the distance driven is 20 times 1, so it's 20. If t is, let's say, 3, then the distance driven is 60. And generally, if t is t, then the distance driven is 20t. That's our formula. Okay, let's plot the first 3 points. If I make a scale 1 here, 2, 3, and so on up to 5, I need to be able to see 20, 60, maybe 80, maybe 100 on the vertical scale. So it will be good to assume that 1 unit on a vertical axis represents actually 20 kilometers. So that will be in kilometers. And the time will be in hours. Okay, since this is 20, this will be 40, that's 60, and so on. So 0, 0 is here. Now 120 over there, 360, that's the point. And if we want to check, let's say, how far did we drive after 5 hours driving with just 20 kilometers per hour, 5 times 20 will be 100. Okay, 100 would be over here. Now this time we chose only a few points to see how the graph may go. But we also know this relation as a linear relation. Distance is directly proportional to the time. So we may expect that the graph of this relation will be a line or a piece of line. Therefore, we don't need to check all infinitely many points. It's enough to check a few points and then just connect those points because all other intermediate points will belong to this line as well. Let's say if someone has been driving 1.5 hours, it will cover the distance 30 kilometers, which is over here. This relation has a very particular property. For every input, we have exactly one output. It is exactly one value that we can attach to every input t. Now let's look at the more formal definition of a relation and some of its properties. A relation is any correspondence between the elements of the set of values of the independent variable and the elements of the set of values of the dependent variable. So any correspondence between independent and dependent variables is a relation. Now the set of independent variables is called domain. That's the set that we pick our input from. And the set of dependent variables is called range. That's the set that we pick the values from. If a relation has such property that for every input from the domain it assigns a unique output value from the range, then such a relation will be called a function. And example 4 represents actually a function because for every input we have exactly one output. Now we can go back and try to identify domain and range for each of the above examples. For instance, in example 4, what was the domain? That means the set of all possible inputs. Since we are not using negative time, the domain is actually from 0 to infinity. So here I would say domain is from 0 to infinity, not because this formula wouldn't work for other numbers, for negative numbers, but just because we're talking about real life situation and there's no sense to talk about negative time before we even start driving. Okay, so that's domain. What's our range? The range is the set of outputs. So what kind of distances we can cover? Again, from 0 to the infinity. So as you see on the diagram, the range will be found on the vertical axis, while domain on the horizontal axis. So range is also from 0 to infinity in this case. Let's go back to our previous slide. And starting from the very first example, what is the domain here? Well, domain is connected with the input, the set of input values, that's the domain. So in our case, domain is the set of all postmen in Abbotsford area. And the range is the set of all possible output values, so that's the range. In our case, the range is the set of households in Abbotsford area. Since there's many households assigned to each postman, this is not a function. In the second example, the domain contains all first coordinates of our points. But observe this first coordinate. The first coordinate of any point on this vertical line coming through 2 is just 2. So the domain, in this case, is a one-element set composed of just 2. What about the range? Well, the range can be anything on the y-axis, that means all real numbers in this case. We can place any real number on the second coordinate. We gave examples of just integers on the second coordinate, but points like 2, 1.93, or any other real number on the second coordinate also belongs to the vertical line coming through the point 2. So again, since there is many values assigned to the input 2, this is not a function. Okay, let's look at the third example. What is the domain for this particular relation? Again, if I look at this relation given as a set of ordered pairs, I am picking the first coordinates of those ordered pairs. So the domain is a set composed of 1, 2, 3, and 5. If I look at the graph in the system of coordinates, in order to see this domain, it's enough to project all the points of the graph onto the x-axis. And those are the points that will be shadowed, that will be covered by this projection. So 1, 2, 3, and 5, exactly the same points as you see. In the case of arrow diagram, the domain are those points that will have at least one arrow going out. So we have arrow going out of 1, out of 2, out of 3, and out of 5. We don't have arrow coming out of 4. So 4 is not in the domain. Okay, let's see the range. Range, again, is the set of all possible values. So in this case, those are the y values, all possible y values. Let's list them. It will be 1 and 2 and 4 and 5. Now, in the system of coordinates, to see the range, we also project all those points, but onto the y-axis. And we look at the shadow on the y-axis. So it will be this point, that one, and that one. Yes, again, 1, 2, 4, and 5. If we look at the arrow diagram, a point will belong to the range if an arrow is coming into it. So for example, number 2 and number 1, because arrow comes to this point, and number 5 and number 4, but not number 3. Since the relation has 3 different values assigned to number 2, again, it's not a function. Okay, so we know what's a relation, and we know that certain relations are functions. A function is such a relation that assigns a unique output value from the range for every input value from the domain. Let's see this example. Here we have a relation f given by arrow diagram. From every input there is only one arrow coming out, which shows us a unique assignment of numbers from the range to every member of the domain. So that's a domain set and that's a range set. Therefore, such a relation is a function because we have a unique assignment. The fact that we have two arrows pointing out to the tree doesn't contradict the definition of a function. Yes, we may have the same values for different inputs, but we can't have two different values for the same input. So let's look at the relation H. Again, domain is here and consists of 2 points, -2 and 3, and the range consists of 2 points, 1 and 0. This relation is not a function because for the input 3 from the domain of the relation, we have two values assigned to it. We have 1 and 0. So such a relation is not a function because we don't have this uniqueness of assignment. How do we recognize in different situations if a relation is a function? We already had some examples, but now I would like to organize what we know in a table like this. Here in the column we have correspondence given by either a set of ordered pairs or arrow diagrams or a graph. In the second column we're going to talk about test for being a function, how to test it, how to determine if this particular relation is a function or not. And in the last two columns we'll try to figure out what's the domain and range for the particular example. So the first example consists of 3 points, 3 ordered pairs of numbers. How do we decide if this relation is a function or not? Remember, a function has to have a unique value assigned to each input. So we must have no 2 pairs that will have the same first number and different second number. But in this case, we have 2 pairs with the same first number, the same input, and 2 different outputs. So that makes it not a function. So I will just write not a function. What's the domain? To get the domain, we're looking at the first coordinates only. So the set of first coordinates is -3 and 2. To get the range, we're looking at second coordinates of the ordered pairs. So in this case it's 1 and 0. We can write it in order 0, 1. Okay, let's look at the second example. Again, to test if it is a function or not, we're searching for 2 pairs with the same first coordinate, but there isn't any. All first coordinates are different. Therefore, yes, that's a function. And again, the domain is the set of first coordinates, so it's -3, 2, and 3. And the range is the set of second coordinates, so in this case just one element, 1. Okay, let's look at the next example. Here we have arrow diagram that indicates certain relation. Is this relation a function or not? Well, if you look at the arrow diagram, what we use for the function test is look at the inputs and see if there is an input that will have more than one arrow going out. If more than one arrow is going out of the input, then this is not a function because the range values are not assigned uniquely. There is 1 assigned to -2 and 0 assigned to -2, which makes it not a function. What's the domain? Well, domain is everything that we see in the first set. So it's -4 and -2. What's the range? Everything what we see in the second set. So in this case 1 and 0. Okay, next example. I'm sure you can do it on your own this time. So pause the video and try. Is that a function or not? Since from each input there's only one arrow going out, then yes, that's a function. What's the domain? Obviously all 3 of those points. So 78, 88, and 89. And finally range. This time range consists of two letters, not numbers, but letters, B and C. The next example shows us a graph in the system of coordinates. So, to test if a graph represents a function, it's enough to take a vertical line and basically move in your mind this vertical line throughout the whole graph from the left to the right. If at any moment you notice that a vertical line is crossing the graph in more than one place, then such a graph does not represent a function. This is only relation, not a function. So vertical line test is very useful and actually quite easy to apply. Think about a vertical line and move it throughout the system of coordinates. If during this move, at any instance, the vertical line will cross the graph more than once, then such a relation is not a function. Therefore, this ellipse is not a function, it's just a relation. How do we see the domain having a graph? Again, as I said before, we project the graph onto the x-axis and see what will be shadowed. So in this case, the shadowed part on the x-axis will be from -4 till 4. Therefore, to record the domain, we need to use an interval, because all points needs to be listed from -4 to 4, and the only way to list those points is to use interval from -4 till 4 with the endpoints, because the graph comes exactly through them. What about the range? Well, to see the range, we actually project the graph onto the y-axis. So starting from the bottom, if I project all those values onto y-axis, what will be covered? Everything from here to there. Okay, the range is everything from -6 till 6. Okay, so an interval from -6 to 6, inclusive. And one more example. Again, a graph is given. If we use vertical line test, no matter where we place the vertical line, it will always cross the graph only in one point. So that means we deal with a function. Yes, a function. Vertical line test holds. So what's the domain? Imagine if we project our graph onto the x-axis, actually every single value on the x-axis will be covered. Therefore, the domain of this function is all real numbers. So we can record it as capital R. Similarly with the range, if I will project this graph onto the y-axis and see what kind of points will be shadowed on the y-axis, it happens that everything will be shadowed. So again, the range is all real numbers. Let's look at some other examples. This time we don't have any diagram. How can we recognize if a given equation represents just a relation or if it's a function? Basically, let's recall the definition of a function again. To be a function, we must have only one y value for every x value. But in this case, we have absolute value of y. So this gives us duality. For example, a point 1 for x and 1 for y would satisfy such equation, but also point 1 for x and -1 for y would satisfy the equation as well, because absolute value of either 1 or -1 is still 1. That shows us that we don't comply with the uniqueness of assignment. For the input 1, we have two values assigned. Therefore, this is not a function, it's just a relation. What can we say about domain of this relation? Well, those are all possible x values, but x is equal to absolute value of something. Well, absolute value of something is never negative, it's always positive or 0. Therefore, the x's cannot be negative, so our domain is actually from 0 to infinity. What about the range? What kind of conditions or restrictions do we have for y? Actually, nothing. Y can be any number, we can still take absolute value of it. Therefore, the range is all real numbers in this case. Let's see the next example, y equals 1 over x. Okay, is that a function or not? Do we have exactly one y value assigned to each x? Yes, we do. If x is any number different than 0, we can always take a reciprocal of this number and obtain a unique value. So there's no problem here. Yes, it's a function. However, if we look at the domain of this function, what we can't take is 0 for x. We can't divide by 0. Therefore, the domain will be every single real number except for 0. So we can record this as all real numbers minus, we subtract sets, a set composed of 0. Everything else is fine. Now, as a matter of range, in this particular case, it's probably easier if we try to graph it. How this function may look like? Well, that's a reciprocal function. So if x is 1, the y is 1. That's the point. If x is 2, the y is smaller, is 1/2. And then for x3, 1/3, and closer to the x-axis. If x is 1/2, then the reciprocal is 2. If x is 1/3, reciprocal is 3. So we get closer and closer to the y-axis. Reciprocal function looks like this. That's one branch of it. And you can check that the other branch, for negative numbers, it will have the same shape, but the graph will try to approach x and y-axis in the third quadrant. So that's the approximate graph of reciprocal function. Therefore, we see that the only value that is actually not taken is 0. We could also observe it by analyzing the formula, because a fraction 1 over something can be as small as we want to, but will never be 0. It's always 1 over something, 1/5, 1,000, 1,000,000, but it's not 0. So again, the y value will never be 0, but it can be any other real number. So range is also all real numbers, but not 0. Obviously, this box is the same as above, so it should be written exactly the same in both cases here. And finally, y equals root x. Let's look at the domain first. What kind of values we can take for x? Only positive or 0. We can't take negative values because root of negative is not defined in real numbers. Okay, so the domain is from 0 to infinity. We also know the shape of this relation. I'm sure we graphed this before. If x is 0, then the value is 0. If x is 1, then the value is 1. If x is 4, then the value is 2, and so on. So we join those points and the graph of root function looks somehow like this. While having a graph, it's easier to look at the range. If we project this graph onto the y-axis, everything will be taken from positive part of the y-axis, but the root will never be negative. Can we have 0? Yes, we can. Root of 0 is equal to 0. So y value can be 0 or anything positive. Again, from 0 to positive infinity. And finally, is it a function or not? Yes, it is. If we have a graph, we can easily see that any vertical line will pass the graph only once, or not at all. But if we just look at the formula, taking a value for x from the domain, that means any positive real number or 0, we can apply a root to it, and the answer will be unique, will be just one answer, because root is defined in a unique way. Remember, that's why when we defined a root, we used the principal root, not any root, and principal root means the positive or 0 value. So yes, this is a function, and we know the shape of such function. It's half of sideways parabola. Okay, let's practice some questions on your own. So pause the video and try to do those questions, and then check with my answer. Decide whether each relation defines a function, then give its domain and range. Okay. We have a set of ordered pairs. Do we have two pairs with the same input? No. Therefore, this is a function. Yes, a function. Okay, so what's the domain of this function? Instead of writing the full word domain, I'm going to use just D for domain. Domain is the set of all inputs. So we have -3, 1, 2, and 3. And then range is the set of all outputs. So we have 1, -3, 0, and 1 again, but we already took the 1, so we don't need to repeat it. That's the set, 3 values in a range. And another question, This time we have a graph. Is that a function or not? Well, let's use the vertical line test. Any vertical line passes the graph only once, so yes, it's a function. The domain of this function is, well, let's project all the values on the x-axis. Remember that the graph is not stopping here, it's actually going farther. If it would stop, we would have a dot indicated, either hollow dot or filled in dot. But if it's not, that means this graph is proceeding. Therefore, all values will be actually covered on the x-axis and to the left as well. Therefore, the domain is all this set, all real numbers. Okay, let's record this, all real numbers. Finally, range. This time we project our graph onto the y-axis, so everything here will be covered until this point. That's a point 2. So from minus infinity until point 2. So we need to use an interval from minus infinity until 2, including the 2. And a couple more examples. Here we have a relation given in a table of values. So again, it's a function or not. Do we have two pairs with the same input? No. Therefore, this is a function. For every input, I have exactly one output. Okay, what's the domain of this function? The set of all inputs. That means -1, 0, 1, and 2. And what's the range? The set of all possible outputs. So 1, -2, this one was already taken, and -1. Take another example. Is this a function or not? If I take this vertical line, it passes the graph in two places. That means this is not a function. It's just a relation, but not a function. Still, we can talk about domain and range. So domain are all those points that will be marked on the x-axis when you project the graph perpendicularly onto the x-axis, right? So all these points are in the domain. That will be -1, 1, 2, 3, and 4. Okay, let's list it. -1, 1, 2, 3, and 4. And range, going to erase the vertical line. The range we can read from y-axis after projecting all points from the graph onto the y-axis. So all those points will be taken, meaning -2, -1, 0, 1, and 2. So -2, -1, 0, 1, and 2. That's the range. In the next example, our relation is given by a formula. Is that a function or not? Well, since this is a square root of something, no matter what the x is, we can always multiply by 2 and subtract 1 and then take square root as long as this x was from the domain. That means as long as 2x minus 1 is bigger or equal than 0. So yes, this is a function. Now, to get the domain of this function, what we need to do is look at the radicand and make it bigger or equal 0 and solve this inequality. So we're looking when 2x minus 1 is bigger or equal 0. Let's solve it. 2x bigger or equal 1, therefore x must be bigger or equal 1/2. Therefore our domain starts from 1/2, and any number that is higher than that would be good. Now, what about the range? Range is always a little bit harder to figure out. But let's try to analyze our expression. Since the radicand, the whole expression 2x minus 1, can be actually any number from 0 to infinity, then when we take square root of 0 is still 0, and square root of something positive is still something positive. And it can go as high as we want to. So the range is from 0 to infinity. We can probably see it better if we actually graph this function. In a system of coordinates, the graph of this will start from 1/2 because that's the beginning of our domain. So let's say if this is 1/2, point 1/2, 0 will belong to this relation. And if x is any higher number, Well, we'll have the shape of root. And we remember the shape of root goes somehow like this. Obviously, I'm not doing it to the scale, just a general idea how the graph may look like. But then it's a lot easier to see that yes, indeed, the range is starting from 0 and going until infinity. If I project those points onto the y-axis, any single point will be covered from 0 to infinity. So yes, indeed, the range is 0 to infinity. Let's see the next example. Is that a function or not? Well, it looks like it's reciprocal, and we know that a reciprocal expression is actually a function. The graph of it has two branches, kind of like this. It could be moved, could be stretched, but it has this shape somehow. So maybe even before we try to graph it, let's see what's the domain. If we have a formula, the domain is easiest to determine. Just by looking at the expression, if we divide by something, we need to protect the denominator not to become 0. So the condition that we need to keep is x minus 5 must be different than 0. Therefore, x by itself must be different than 5. Any other number than 5 is good. So the domain is all real numbers, but not 5. Okay, if I already have my domain, I know that point 5, let's say it's here, is the tricky point, is the point when our relation doesn't get any value. So this point will actually indicate that we have a vertical asymptote here. And the horizontal asymptote should be at 0, because 5 over something will never be 0. So we must have a horizontal asymptote coming through the 0. Therefore, the shape may look somehow like this. If this is hard for you to graph, you may even want to plug it into the graphing calculator and see how it looks like. Confirm it, but try to build your intuition how the asymptotes may look like, how the graph may look like. Check some points if needed. Now, if we have this graph, but also if we look at this expression, what can we say about the range? Well, in the range, I may have 5 over something, but 5 over something will never be 0. It will be always 5 over a certain number, which is other than 0. So the range is all real numbers, but not 0. And we can also see it on the diagram. All values, all real values can be taken, except for 0 because we have a horizontal asymptote there. So finally, when we know a little bit more about this expression or its diagram, we can decide whether this is a function or not. Well, first of all, the vertical line test indicates that yes, it's a function. Secondly, just looking at the expression, if I take any x value, I can always subtract 5. And as long as this x minus 5 is not 0, that means as long as we are in the domain, I can divide 5 by this value and have a unique answer. So yes, it is a function. Finally, a strange relation like this, x plus y is smaller than 3. What can we say about it? Is that a function or not? If I have an input, any input, let's say if my input is 0, what do I get here? Well, I get the inequality y must be smaller than 3. But there's infinitely many y's that are actually smaller than 3. Well, it could be 2 or 1 or 0 or 1.5 or -3. So we have infinitely many y values that can be assigned to this particular x value. Therefore, this is definitely not a function. And basically no inequality can represent a function. It can only be a relation, because remember, in any inequality situation, like in this case the related equation would be y equals -x plus 3. So it will look somehow like this. Broken line just because the inequality doesn't have equation. And then when we need to shade the region that satisfies this inequality, it will be here. You may check on that. So as you see, if we take any vertical line, it crosses the graph infinitely many times because the graph is composed of entire region, not just one curve. So inequalities are not functions. Those are only relations. But we can still talk about domain and range. So what's the domain for this particular inequality? Well, if we project this graph, the shaded region, onto the x-axis, everything will be covered. All the stuff, all those values will be taken. Therefore, the domain here is all real numbers. And what about the range? What do you think? Well, let's project this graph onto the y values. Again, everything will be taken. So entire y-axis is the range. Okay, the range is also all real numbers.